Thanks. Thanks everybody for coming. So I guess the title is Weak Lower Bounds on Circuit Synthesis. Imply strong complexity separations. So the title of the paper is about so-called resource-bounded compression. So what we do in the paper is more general than what I'll talk about, but I feel like the circuit synthesis problem by itself is pretty general and of a lot of interest recently. So this is joint work with Dylan McKay and Cody Murray. Okay. Right. So the main problem in this talk, so I'll put it somewhere far enough away so that hopefully I won't erase it, is the minimum circuit size problem. So MCSP. We are given a function, Boolean function, and think of this as a truth table of length capital N, which is 2 to the n. Okay, and we're also given, let's say, integer parameter s, and s is say between 0 and 2 to the n over n, and we want to decide if f has a circuit of size at most s. Okay, and there's also a search version of this problem where you want to output such a small circuit or output fail if there is no circuit. Okay. So this is a very canonical compression type problem. I give you some string of 2 to the n bits, and I want to know, does it have a succinct representation? Okay. But it's a much more feasible version of universal compression than, say, Kolmogorov complexity, which is in general uncomputable. So this problem, MCSP, is an NP, namely because I give you the whole truth table. The input is of length 2 to the n. So I can always guess a circuit, let's say in this regime, and try on all possible 2 to the n inputs to check whether it computes the function. Okay, so because the input is so large, you give this big representation of the function, it is actually an NP. And the question of whether it's NP complete is somewhat infamous. So evidently, Levin was trying to prove that this problem is NP complete and delayed publication of his results due to this. And it's still not known to be NP complete. One thing that we do know is that proving it's NP complete in the usual ways in which we do would imply some kind of advance. So with Cody, we showed that if, say, it's NP complete in the usual many one polynomial time reductions, then that would separate, for example, exponential time from ZPP, so which is still open. So at the very least, proving it's polynomial time in the normal sense would require some advance in our understanding about how powerful randomness is. And there are lots of other results along these lines. This is just one example of such a result. And recently there's been a lot of literature about trying to understand the weirdness of MCSP, because it does look like a rather different problem from the ones we normally think of as being NP complete. So the result of Hirahara from last year, which won FOCS Best Student Paper, says just informally, there's a randomized reduction from worst case approximating MCSP, so approximating the minimum circuit size, to average case approximation to MCSP. So this is very, very intriguing because it offers the possibility of having some NP complete problem with a worst case to average case reduction. And it offers the possibility perhaps of basing cryptography on P not equal NP and things like that. Okay. It is non-black box. It has to be. It actually has to be. Bogdanov and Trevisan showed it has to be, and it's non-black box in a very, very interesting way. Right. So,
what is the factor of approximation? Any factor?
It is something like within some factor of like maybe 2 to the epsilon n for some constant epsilon. So 2 to the epsilon. So approximating it. I think
into
maybe
the epsilon in terms of
into the epsilon for some constant epsilon. Yeah. So this is little n. Yeah. Little n. Yeah.
What is the average over? It seems like for a random function, the answer is 2 to the n over n, no?
Yeah. So what you want to do is, so average case approximating MCSP roughly corresponds to what Rosbroff-Rudish called a natural property, useful against small circuits. So what you want to do is say, like, I distinguish the things which have small circuits, like really small circuits, from the random things. The thing, like, but I'm allowed to on random things sometimes accidentally say easy. But I always say like easy on like the easy stuff, but on the really hard stuff, like the random stuff, I say hard most of the time.
So is it average case?
Because on most of the inputs I say the right answer.
But something that always says hard is also gonna be okay.
Yeah. But it's according to this criterion I was saying. Yeah, exactly. To make it non-trivial, you have to look at the criterion I was saying.
A random easy one and a random.
Yeah, you can think of it that way. Yeah.
So when you say it's non-black box, I mean it is not using the usual polynomial kinds of worst case or average case.
It's not using the normal stuff at all. Okay. It's very, very different. Yeah, there is no like lifting to a multilinear polynomial or low degree polynomial at any point. No. Yeah, there's no trick of this kind here. Yeah, it's something very different. I just want to, give you like one example of a result which is like among this big line of work trying to understand the difficulty of this problem. Okay, so we'll look at in this talk sort of parameterized version of MCSP. So it's a very natural version. So you think of S is some function from natural numbers to natural numbers. And so now we're given f as before of length capital N to the n. And we want to decide a circuit of size at most S of n. Okay, so now the circuit size is given to us as part of the problem definition. Right? And there's also a natural search version of this problem where you're supposed to output a circuit if it exists, or output some special string that says fail. Okay? So this problem is already believed to be intractable already for small S of n. So just an example follows from like Rosbroff-Rudish that under standard assumptions, okay, I won't go into them because there's lots of other cool stuff to say. Under standard assumptions, MCSP, there exists a C, so the MCSP and the C is not in p-poly. The basic idea is that if MCSP and the C were in p-poly, then this would give a p-poly natural property useful against size into the C, okay? Which under standard sort of pseudo-randomness assumptions, say in cryptography, is strongly believed not to be true. So we already believe that this thing is not in a p-poly already for small sizes. And so the question is like, well, how hard is it to prove any kind of lower bound on this problem?
Wait.
So, yeah?
That is a believable assumption?
No.
You can break any one.
Yeah. So it's not believable.
Oh.
So the point is that like if the negation of this were true,
Okay.
then this would be true. Yeah. So, okay. No.
Yeah.
That means like yeah. No. Yeah. Definitely not so believable. Right. So okay. So what do we show about this problem? So it's believed to not even be in p-poly. We'd like to know like what's the difficulty of proving kind of any lower bound on it. So this is the kind of stuff we show. So one is that we get very efficient algorithms and circuits for this search version, actually, of MCSP, S of n, when, say, S of n is like sub-exponential. So I have a circuit of, I'll give you an input of size 2 to the n. I want to know if it's a circuit of size, say, 2 to the n over log n. So we get very efficient algorithms given some oracle in the polynomial hierarchy. So assuming I have some oracle in the polynomial hierarchy, I can get very, very efficient algorithms. And the oracle calls to this thing are not very big either. Okay. So you can think of it as some kind of algorithmic result, assuming you have things for pH, but it has many sort of strange corollaries. So in general, they say things like extremely weak MCSP lower bounds in this kind of regime, the size is not too big, implies like P not equal NP and all kinds of other good stuff. You know, so like all the other replacements for P not equal NP. So other good stuff. So like in other words, I'm talking about like lower bounds where you're just saying it doesn't have like an n times pi log n time algorithm running in pi log space. So ruling out that kind of thing for say MCSP into the C would already imply P not equal NP. So and we believe the thing is not NP poly to begin with. Okay. All right. So
the non-search version is an NP, right? So
yeah. The
difficulty is just to do the search.
So no, what I'm saying is that like if you have like a very, very weak lower bound. So if I prove MCSP is not n to the 1.1 time.
And just the first version, just the statement of the theorem.
Yeah. So this also holds for search. Yeah, the search version.
So without the search, the first statement would be really true.
Yeah. So no, what makes it non-trivial is that the size of the oracle calls are not very big.
Oh, I see.
So like I'm at so yeah. So the point is that like I'm consulting an oracle, but I'm not like asking it to solve the whole problem. I'm consulting it on things like almost of this size. S of n. Yeah. So that's why you get these kind of weird corollaries. So it's like you get into the 1.1 lower bound on MCSP. In certain regimes, you already get P not equal NP or something. You know, so it's some kind of weird connection. In the paper, we show similar results for other compression problems like time-bounded Kolmogorov complexity, but I'm going to focus on MCSP here. Is there a clock? All right, let's see. There's my clock. Okay, good. Very good. But before I get into it, I want to say like, we had these results for several years, and we didn't write them up because we struggle with the question, what do they mean? Like, do we expect to prove separations like P not equal NP in this way? No, I don't expect to prove a separation because I have some extremely weak MCSP lower bound. Is this some barrier to proving lower bounds for these kinds of problems? Because if we could prove them, we would get, P not equal NP and other stuff. I don't think that's a good story either because it doesn't imply anything we don't already believe to be true. It seems strange to call something a barrier if it only implies true things. So the other barriers do not have that property. The other barriers imply things we believe to be false. So I don't think of it as some kind of barrier. So what they do show, so we're not sure what they mean, okay? This is like one of the few papers I wrote where I didn't actually know what the story was. And the program committee somehow liked the paper, even though I just said, I don't know what the story is. I mean, that's I just like intellectual honesty, you know, like for once it actually paid off. Okay, so what does it actually show? Well, it shows certain like weak lower bound problems sort of already contain the difficulty of way more evidently difficult problems, supposedly. So they already complain the difficulty of like P not equal NP, NP not NP poly, and so on. And so that is definitely true. And the main thing, I guess, is that it's just intuition breaking. Like, I mean, complexity theorists spend years trying to build intuition about, you know, what lower bounds should be true and what is like the degree of difficulty of proving this over that, so you know, we can figure out like what to try to say next. And this sort of says some kind of gap theorem about that, I guess. Yes?
So maybe it's worth mentioning that there are other escalation results in other models where superlinear lower bounds imply exponential lower bounds. And you know them in arithmetic circuits, and some very old ones.
Sure.
And in all of them, it seems like there is some compression results that say, well,
Yeah.
Right, so
Yeah. You can think of it this, yeah.
So it's in the same spirit.
Sure. Yeah. I guess, yeah. What's going on here is it's something in the Boolean world. Yeah. Somehow. Yeah.
Even in the Boolean world, I think Eric had a result of that.
Well, not quite the same.
Not like this, yeah, but I mean the spirit is superlinear lower bound implies exponential.
Yeah. So.
I mean, you've got some results like this where you can actually prove lower bounds for other problems, right?
Right. So the point is, it's not like MCSP lower bounds are hopeless.
Right.
Like, for example, we know that even when MCSP is say say 2 to the square root of n, you can get a cubic formula lower bound. This is something recently proved. It was on ECCC recently. And so the known lower bound techniques do seem to extend to MCSP in almost all the different dimensions you can imagine. And then people are just sort of reproving these things, like the best known formula lower bound, the best known branching program lower bound, and so on, for MCSP in this kind of regime. And yet, getting something. So these are not like get a formula lower bound of size the 2.99. Otherwise, we would be celebrating, I guess. No, there is something like, but even getting like n times pi log n size lower bound with order log n depth would already imply like NP naught in C1.
But these are lower bounds we don't know for any function.
Exactly. Yeah. We don't know, but yeah, at the same time, the intuition would be that should be an easier problem than proving the whole thing. Right? So I guess the point is that for certain problems, it's not. It's no easier than just proving the whole thing.
You also mentioned something about the streaming model.
Yeah. I'm gonna state all the theorems. I haven't said any theorems yet. I'm just this is like whatever high level stuff, right? So I guess the one bottom line we can say is that we need to study these problems more carefully. Okay, so let me say the first theorem, which is a special case of what we prove in the paper, and it says for sort of nice functions S of n, so like time constructible stuff, there is some oracle A in the polynomial hierarchy, and an A oracle streaming algorithm, okay, for MCSP on this circuit size S of n. With the following properties. All queries to A are small. They're of size O tilde S of n. So this is a polylog factor suppression. So the algorithm uses space O tilde S of n. And the update time. So in other words, I'm going through this stream. Let me draw a little picture. I'm going through this stream of length 2 to the n, and I have my little streaming algorithm, so alg, and I'm only going to spend a certain small amount of time on each bit, and I call it the update time, and it's only like order O tilde S of n. So that means the total running time. So total time is like n times, let's say O tilde, capital N times S of n. So this is capital N. Okay. So, right, if I could ask you something about the entire input, then this is obviously trivial if I just take the problem like the Oracle solving MCSP for me. But here the queries are very small. They're only as big as the circuit size itself. Okay, so this streaming algorithm is going to have a small amount of memory, basically just enough memory to hold a circuit of size S of n in it. It's going to just pass through the input and update it bit by bit, call these queries. At the very end, it will either output minimum size circuit or output failed. There is no circuit correctly. Okay. Any questions about like the thing? Yeah.
It's not approximate.
No, it is exact.
Exact answer.
Yeah. So, right. Yeah. When I talk about related work, there is a lot of related work about like saying if you have weak lower bounds in the exact or average case, things like that, then you would get these kind of things. Yeah. So what we get is actually just the usual exact case, worst case, so on.
So how weak is weak?
I will say very precisely, yeah.
So this is for any SN?
Yeah, it needs to be, something, say, time constructible, so that like this algorithm runs in decent time. So because it need to be able to construct what S of n is.
All functions,
Yeah. So that's what I meant. Nice.
If we give the Oracle to some crazy class, would this be easy? I mean, it seems that the compression is the thing, right? You compress the input to give it to the Oracle. Why do we do pH?
So what kind of Oracle would you prefer? So the reason why we do pH is that if P equals NP, then A is in polynomial time. So maybe it will make more sense when I state what the corollaries are.
I'm asking about like something stronger than pH. Would it be clear?
Yeah, it's clearer. It's clearer if you say use P space. In fact, I think in my proof I will just talk about
So how do you do it?
P space.
Okay.
Well, I have to like. There's lots of other stuff to say before I say that. Yeah. It's okay. It's okay. Yeah. So I want to state some corollaries of just this result, which are pretty immediate once you have this thing. So one corollary is that, so if P equals NP, then for all these nice S of n, this search, actually says this search MCSP, S of n, has a streaming algorithm, and it runs in poly S of n space and the same update time. So poly S of n space and poly S of n update time. Okay, and the proof is very simple. I'll go ahead and put it here. P equals NP implies pH equals P, so our oracle is now in P. So we just replace A queries with an algorithm running in poly S of n time. Okay, because the inputs to this are only of size O tilde S of n. Right, so I have a polynomial time algorithm for A, so it does poly S of n time. Right, of course, poly S of n time only means poly S of n space. So it's only poly S of n extra space. Update time is only, so everything you just multiply by some poly S of n in the worst case. All right? Right, so the total time is O tilde times poly S of n. All right? Okay, so a corollary of that is that very, very weak lower bounds for MCSP S of n, even search, even lower bounds on constructing the circuit synthesis problem, is going to let me, so even very weak things will imply P not equal NP. I'll give like two cases of that. Let's see. So first, like, say MCSP into the 100, if it's, say, not in n times pi log capital N time and poly log capital N space, then P is different from NP. Okay. This is just taking the contrapositive, right? So so just taking the negation of this implies this, right?
And that's even for a streaming algorithm.
Yeah. By streaming out. So yeah, that's a very good point, because there are a lot of problems that are not solvable in pi log n space with the streaming algorithm. For example, the set XX, such that X is a binary string. This is not solvable even in sublinear space.
What is it called? F?
XX, such that the language.
Oh, it's XX, I see.
X such that. Yeah. So it's not hard to prove. Prove in my undergrad automata course. This takes a streaming algorithm requiring linear space. So there's easy to come up with like very simple languages that require a lot of space. Of course, like here, right? This is log capital N to the 100, right? So the witness size to this problem is only log capital N to the 100. Okay. So there, it's not like it's extremely mysterious why proving a larger space lower bound than say log n to the 100. So in other words, you can't get any polynomial factor here. Say for that would imply like something interesting, because you're saying even if when I give you more space than the amount of non-determinism, I still get a lower bound. But it's interesting that like even this kind of setup would already separate things in a major way about like, even though we're not, this is obviously not talking about time or space. Sorry, it's not talking about space. Bound it like. Okay, so another setting, for example, is like, let's say MCSP 2 to the n over log n. So just take like some unbounded function of n here. So if it's not in to the 1 plus epsilon time into the epsilon space for some epsilon, then we would still have P not equal NP. Right, so if you take a circuit size that's like 2 to the little o of n, and you manage to prove so concrete into the 1.1 time into the 0.1 space lower bound, this would also imply P not equal NP. Yes.
This problem, the streaming version, has a fully log n space algorithm if I don't care about time at all?
Yes. Well, it's a consequence of this thing. Yeah. Because you could just brute force the oracle. Right. If you don't care about time, you could just brute force solve the oracle in small space because it's pH is NP space. Yeah. So there is something if you don't care at all about time, but it like brute forces over all the possible circuits. So yeah, like this. Yeah, this thing always has an Sn to the order S of n times say to the order n time algorithm. Right, this one. Just by trying all the possible circuits of size S of n.
Streaming also at the same time.
Sorry?
That thing should be streaming also.
Trying
everything is not.
Yeah. You can. Yeah, you can also do that brute force in every single step to brute force. Yeah. Like if you're calling the thing in every step, right? Okay, so. Right, so you get meaningful results here even up to like 2 to the n divided by poly n in the circuit size. Okay, so that's something we can say about streaming. So also for oracles in a circuit we can say something. So, and this is where you get like extremely weak circuit lower bounds imply things like NP, not NP poly. So theorem 2, special case in our paper is, so we let L of n be some parameter, we just say at least S of n squared, and at most 2 to the n. So when you say there is some oracle in Pich, a different one, and a uniform, let's say AC, so unbounded fan-in or an AND circuit family, okay, for this search MCSP problem on S of n, but it has like B oracle gates in the circuit. Right, so it can have like some calls to B, some calls to B, but we're going to restrict the fan-in of these calls to B. So it'll have like some and some ORs, things like that. But it'll have the following properties. So first, for n-bit inputs, the circuit has depth, order log n over log L of n. Okay, so it's low depth and size n times S of n squared. So it has low depth and small size. And the B gates have fan-in at most, say O tilde L of n. All right, so here, so we think of L of n as still being very small but slightly larger than the circuit size. So all these things have got L of n size, the whole thing is say n times S of n squared, and the depth is not very big. Say log n divided by this log L of n.
So what's a B gate? It's like the query is the string that is specified by the wires?
Yeah, so a B gate takes in a string and it just outputs 1 if and only if that string is in B.
Okay, so all the wires are like specified.
Yeah, so I've got some X and I'm asking whether X is in B. And it outputs 0, 1. That's what a B gate does, yeah. Okay? Okay. Right, so we get these very efficient, sorry. Okay. Yeah, so we get these very efficient circuits provided I have oracle access to something in the polynomial hierarchy. And so as a consequence, if say MP were in a class like P poly or TC0, we would get like hyper efficient circuits for this kind of problem. So, so here's some interesting corollaries. So I'll just sort of write them here. If MP is in say TC0 or ACC0, then this search MCSP on say 2 to the epsilon n size for any fixed constant epsilon is in TC0 or ACC0 of constant depth and n to the 1 plus little o of, sorry, big O of epsilon size. Okay, so it would be constant depth, say 1 over epsilon depth, and n to the 1 plus order epsilon size. All right, so well, for a fixed constant epsilon, the witness size is only some polynomially smaller than the input. And we're saying, right, if you have MP and TC0, you actually get these like very efficient circuits in this case. So the contrapositive, again, is proving a lower bound of like a TC0 or ACC0 lower bound for this kind of size against finding a circuit of 2 to the epsilon n size would just separate MP from TC0. Okay? Right, like we would expect, like saying, if you prove that like for all polynomials you don't have a constant depth circuit, then yes, of course, MP is on TC0 because this thing is an MP. But here we're saying, in fact, like for smallish circuits, and even like very close to linear lower bounds would imply the result. So this is something you get from setting, say, L of n to be, let's say, 2 epsilon n S of n to be 2 to the epsilon n. All right. So that's one kind of corollary. Another one, probably if I write any lower, it won't be readable. Actually, is this even readable to everybody? Oh, it's readable to you. Yeah, it's like totally fine. Yeah. Oh, I guess there's also a poll. Okay. Yeah. Okay. I can't remove the poll. Oh yeah, I'll just put this other corollary here. Yeah, there's a. Yeah, because of my height, I just can't utilize so much of the board. So another corollary is that if NP is NP poly, then you get this search MCSP S of n problem has in the 1 plus epsilon size and into the epsilon depth for actually, so let me put 2 little o in there. Just little o in. Okay. So this you get from setting this L of n to about into the 2 epsilon and S of n to be so get this capital N to the epsilon. So proving some kind of size depth lower bound for this kind of thing would already separate NP from P poly. But yeah, we don't really know lower bounds of this kind for sort of any problem in NP. You can scale it down a bit more, and maybe I'll just write sort of one more corollary about that, and then I'll start proving how the theorems go. So if NP is NP poly, then this search MCSP poly n, say on poly n size circuits, has n times polylog n size and polylog n depth. And if you go so far and say NP is an NC1, then in fact this depth can be made order log n depth. Okay, so you can creep very, very close to sort of the state of the art in lower bounds. There's some ongoing work with my PhD student Li Ji Chen where we in fact are showing roughly that if you can prove lower bounds for this problem for like slightly larger than cubic size formulas or slightly larger than quadratic size branching programs, you get a huge lower bound of
MCSP.
for this MCSP type problem. Yeah.
So not circuit, but like branching program.
Yeah. So if you just like super quadratic or super cubic formula lower bound would already get some major separations like maybe NP not in NC1 and stuff like this. So, but that's a totally different set of ideas from what I'm going to talk about here. Like, right. So even for these kind of weak-looking things, it actually captures a lot more. And there's a lot other stuff like this in the paper. Before I get to the theorems, I do want to talk about related work. Probably the most related work, the thing that sort of inspired us to finally write this stuff up, is Oliveira and Santhanam from FOCS 2018, and Oliveira, Pich, and Santhanam from last year. So they showed similar results along these lines, but weaker in the sense that they didn't get exact things. So they show that if you have a lower bound on approximating MCSP, say within some 2 to the epsilon n factor, or if you had a lower bound on average case MCSP in the sense that I was describing to Mark, then you could prove big separations like this. So, but it didn't work for the search problem. It was just like distinguishing easy from hard, and it was only in like some kind of so approximation or average case type regime, whereas here it's just some normal worst case exact lower bound. But yeah, they were the bold visionaries who finally like inspired us to write up our own results. Good. Any questions? So I think I will erase everything but the 2 theorems and then go over how to prove, let's say, theorem 1. So how much?
Do you think theorem 1 could be true with linear time, or do you need
Oh,
Like linear size lower bound for polylog depth. Should be-
so what part you want to make linear to?
Just the total. The total.
Actually, yeah, there's some hyper-optimization to you. So in fact, if you look at int time of n versus d time of n for random access machines, that gives you even stronger things. And then you can start talking about like constant factors and logs and stuff like that. We haven't really like looked at that setting up parameters because these parameters were already cool. But if your goal was to try to separate deterministic linear time from non-deterministic linear time, then yeah, you could look at that. And I mean, there should be at least some log factors lying around just because of the complexity of storing a circuit of size s of n. You have to describe it in s of n log s of n bits. So there's some kind of
Yeah, but it can be log if the circuit size is polynomial.
yeah. So you could tune things. Yeah. So maybe it'll be clear from yes.
So in terms of results, so one question is, so the lower bounds are barely superlinear,
Yes.
but for problems for which there is
I don't know if I can use this.
an almost linear upper bound also, or not necessarily.
Sorry.
But
you say it
it's
again?
for problems for which there is a trivial n to the 1.1 algorithm, or even less, or are there settings where this is not the case? So you need barely superlinear bounds, but the trivial upper bound is super polynomial, or
Yeah. So here the trivial upper bound is way
so there is a real
bigger. There is a big gap, at least in our knowledge, right? So like if I'm looking at this MCSP poly n, which we already believe to be super hard, that like in terms of the input length, like capital N, that's like capital N to the polylog capital N. So we don't expect such a problem to be NP hard because it has a quasi-polytime algorithm, but it's widely believed to be hard because we believe in sub-exponentially strong PRGs, stuff like that. So it does have this kind of bound, like for the poly. But then when you get closer to 2 to the epsilon n, then it's like, it becomes essentially exponential time in the original input. So like if this were like 2 to the epsilon n, that's like capital N to the epsilon, and then you're enumerating over 2 to the capital N to the epsilon possible circuits. So that regime, there's really nothing better than an exponential algorithm. And I'm saying into the 1.1, even the 1.1 time lower bound, like streaming small, like into the epsilon space already proves to be like NP. So yeah, there's a gigantic gap in there. Yeah. So there's like this time to solve. Okay. How much time do I have? I keep looking for a clock that's not there. I guess. Okay. So.
It's 44.
Yeah. So I have 15.
Yeah.
Yeah. Just let me let me know when I'm out, when I don't have. So if you're entertained, I guess I'll keep. So let's.
Right.
Yeah.
Just for the purpose of proving this, you might as well assume that the function is a small circuit, right? It's a circuit size s of n. So what you really want the help from the oracle is distinguishing all these possible small circuits and eventually lead you to the one you want.
Yeah.
So the first two properties are sort of not surprising because if this is a space of
Sure.
okay.
Yeah. So the theorem 1 I think is very, very easy, actually, to be honest. Theorem 2 is more complicated. It basically it's like recursive applications of what happens in theorem 1, like to like build up some tree of what's happening in theorem 1. But at least so theorem 1 is something that is hopefully pretty easy to see and whatever. So we'll just argue that there is some oracle in P space, and then for those of you who like pH, you can figure out that it's also in pH. This is still interesting because it would say that P equals P space implies like these super fast algorithms. We don't, separating P with P space is also wide open. Okay, so what's the idea? So we're going to pass over this 2 to the n-bit truth table using this algorithm, and so we want to maintain in memory the so let's say we're at some point here. We want to maintain in memory the smallest circuit we can find, C, that is consistent with all the bits of the truth table so far. So like among all of the possible ways to say extend this thing, we want to say find a circuit that's the smallest possible and consistent with everything up to here. So this thing is consistent with bits seen so far. Okay? That's what we'd like to do. And if there is no circuit that's consistent, like say up to some point, then there can't be any way to complete it to a truth table either, right? Like adding more bits only makes it harder to get a circuit that will satisfy the conditions we want. So at some point, if we can't do that, we just say fail, and we just say fail, 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 fail for the rest of the way. All right, so this is that's the idea. So what we're going to do is we want to think of it as reading S truth table bits at a time. So we'll read S, S, S in like a chunk. So initially, we'll just use our oracle A to compute a C consistent with the first S bits of the truth table. Okay. All right. So we're looking at the first S bits. We can construct some kind of circuit consistent with those, and we'll use A to compute that. Okay. So A is going to guess a circuit, such like some maybe verify its lexicographically first circuit, such that it gives this behavior on the first S bits of this truth table. Okay. But because we're only looking at S bits of the truth table, the queries of size, or the query here, well, I guess we're computing the bits of the truth table. There's multiple queries to sort of figure out the different bits of the circuit description. So size S. Okay. All right. So there's some way we're just going to guess a circuit and then check that it matches up on the first S inputs, and then try all the smaller circuits that are say lexicographically smaller, show that they don't, and output the bit of that thing, like for like some arbitrary bit of this description. Okay. I mean, of course, in P space, this is very easy to do. You just enumerate over all the circuits, right? Until you find the first one. Like in Lexor, just enumerate over all the circuits till you find the first one that's consistent. All right. But yeah, the point is that the query is only of size S. Now, so suppose we're at an arbitrary point. So now we're some arbitrary point in the truth table, and let's say we've got some, say, log n bit counter telling us where we are. Okay, and we inductively assume that either the memory holds a consistent circuit C, consistent with all the bits of the truth table we've seen so far. So in other words, it agrees with all these inputs and has size at most S. Or it says fail if there is no such circuit of size at most S, if no circuit. All right. So then in case 2,
So actually, A is not streaming. A has access to everything so far.
Yeah, A is A is a oracle in PH. So it's going to have all the queries will be of size this. So it actually doesn't have access to everything. It just gets input of size S of n. Okay. So think of S in as small.
It's not reading the tape. A is not reading.
A is not reading a tape. Okay. We're going to query A with stuff from our memory, okay. And because we have whatever small space, we can just do that. So all the queries to A will be written in the memory.
That would
Yeah. Okay. So in this case too, we just propagate the fail, right? If we ever reach fail, we just keep failing, pass over the input, and then just say fail, right? Like we already don't have a circuit up to here. So in the other case, maybe I will use a different color. So the idea is we read S more bits, okay, of the truth table. And so think of these as some input-output examples. So like x1, f of x1, up to x sub s, f of x sub s. Right, so, and they're in consecutive order. So like this is like some binary string. This is the next binary string, the next one, the next one, the next one. All right, and so the problem that we want to solve is we're given an input, a circuit C, and we're given these new examples. Okay, we want to output a C prime that agrees with C on all inputs up to this x1. So on all inputs prior to x1 in Lex order, it agrees with it. And it outputs the correct value on everything in our list here. Okay?
It's not, so just to check, so in streaming algorithms, you don't control what's the order of x, the first coordinate. But here you do.
Here I'm assuming I'm given the truth table in Lex order.
Yeah. So no, but in a streaming algorithm, like the first coordinate is not under your control. The data comes in however it comes.
Well, then just call it one-way.
Yeah, it's
access to
one-way
the
access.
input.
That's all.
Okay.
It's not a streaming algorithm. Yeah, that's what was confusing me. How this
Read
even
once.
works.
I mean, you could, like as long as whatever ordering here is computable, like in some reasonable
That's not a
way.
streaming algorithm.
Okay.
It's a one-way access. As
Okay.
Eric's
Okay.
theory.
Okay. I mean, all right.
Right? You know what I mean? Like streaming algorithm is like, approximately computing the moments and stuff.
I think some people do use the word streaming for the
For this model.
Like it doesn't make sense to talk about a streaming algorithm for XX such that X is that's under your definition. Right? Like that doesn't make any sense. I give you the bits of X in some arbitrary order. What does that even mean?
I
So-
don't think of it as
If
as
you're
like
getting
one-way
pairs
access.
x f of x in some arbitrary
I
order.
guess somehow.
Sorry?
If you're getting pairs x f of x in some arbitrary order,
Yeah. So
that would be a different model.
Yeah. Well, that's
so
streaming
the
model.
point is that like the input is not given to you like this. The input is given to you in bits.
I know.
Okay. I wrote it this way because it might make it easier to picture. This is not the way the input is.
Maybe I'm just showing my ignorance of current terminology.
Okay.
This was called one-way access. That's why.
You can also call it one-way access. Yes. I
Then
agree.
it all makes sense.
Okay. Yeah. So either we output this thing or we output fail. Right? And the observation here is that so this thing has to be of size at most S. Again, in P space, you could just enumerate over all the circuits of size S and check these conditions. Okay? That's it. I mean, so once you do that, then you're just updating the thing one more time. So like you, depending on like what corollaries you're looking at, you might want to encode this slightly more efficiently than that, but that's the basic idea.
So,
Yeah.
You know, there's some upper bound on the running time of the ORCA. If P is equal to NP, now this will run in some fixed polynomial time, right?
Yeah.
So you can take bigger blocks, like take poly S blocks, right? Size blocks. I was thinking if you can get rid of the NSN, replace it with like N plus SN or in the running total.
Oh, you mean like
Next year.
if P equals NP? I mean,
The total, yeah.
In the total, where it says total N times
Yeah,
SN,
yeah,
then you
yeah.
do it N plus SN or something kind of
in
more linear.
plus SN. Yeah. You don't have to take that time. Yeah, depending on how you set it up. Right. I mean, I guess the point is there is some poly S of n overhead of running your arbitrary polynomial time algorithm here. So, I mean, in general, you'll have n times poly S of n, even if you divided by S of n a few times here. But if you had a linear time algorithm for the thing, then maybe you could, just get n. Yeah, but I don't know. I didn't work it out, but
Like linear circuit lower bounds would also imply something.
it's possible. It's possible you could derive that from like carefully looking at
That's
this.
where we start with circuit lower bounds, right? So
Yeah, it's possible you could do that from carefully looking at the argument. Yeah.
So already here, why are you paying capital N times S of n? You're reading S of n bits.
Yeah.
You're doing nothing till that.
Yeah.
And for that, you are spending S of n time, no?
Yeah.
So why it become n times S of n? Why isn't it n divided by S of n?
So because I have to query this thing.
No, I think it's question. You just have to go over the whole input. It's just the capital N is the
No.
length of the input.
Well, he's so because the oracle is a decision problem and it's only outputting a bit. which, you know, I'm sweeping under the rug. So you have to query it like in, you have to query it S log S times. So that throws a S log S factor back in there. Yeah, yeah. So you got to query it that many times for like, yeah. But you could optimize it slightly more. Yeah, yeah. I'm not saying like optimization isn't possible, but right. So that's the idea of that, right? It's fairly straightforward, and this kind of thing could also be done in Ph. Just like you guess the circuit for all the inputs up to this. You check that. You test that. You check that all the smaller circuits don't do that. Things smaller than C prime. So, do I have like
2 minutes?
2 minutes. Okay, I will draw a picture of theorem 2, and then I'll be done. So, so to get these circuits that are like really low depth and stuff, yeah, this is more complicated. The idea is that we've got some truth table of size 2 to the n. We're going to break this thing up first into blocks of, say, size S, and we'll form a circuit, say C1, C2, that's consistent, so 2 to the n over S with each of these blocks, okay? So then my oracle B is going to do the following. It's going to take in L bits, so element, and what it'll actually do is it'll take in L of S copies of circuits of size at most S. Okay? So it'll take in L over S copies of these things. And what's it supposed to output? Let's just say for simplicity it outputs multiple bits. It's going to output another circuit C prime, also of size at most S, okay, which is consistent with this entire part of the truth table that these covered. Okay? So this thing is always taking in L over S circuits of small size and outputting one circuit of small size. All right? Now you have to kind of keep track of the end markers, like so here to here. How many inputs am I supposed to cover? Is it consistent with this one, this one, this one, this one? Again, in the P space, you could easily do that in Ph. You can also guess the circuit and then start checking these conditions. And so in general, you have some L over S airy tree of these kind of things. And so imagine like each of these is outputting a size S circuit, a size S circuit, and so on. And this thing will have depth like log n over log L over S, because of the way we set S, this is at most log L. But yeah, along the whole way, like I'm just recomputing, like compressing, recompressing, 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 recompressing as I go. Okay, that's the basic idea. I've probably exhausted my time now, so stop.
So in the training algorithm,
Yeah.
the order doesn't, I mean, any order would work? If you, I mean, you never use
So this is an interesting question. Yeah. So if it comes in like in arbitrary order, so x and f of x.
Well, the circuit complexity can, well, okay, so you're saying.
It's an interesting question.
The order might not be computable.
Yeah. So let's assume I can't compute the ordering, and it's just coming in. However,
I think
you could still
need some kind of approximate version.
why? I mean, you could still guess a circuit consistent with those things. I mean, I'm not using the ordering.
Doesn't have access to those.
What? I mean, I'm not using the ordering on the inputs in
Well,
a.
but if I'm understanding his question properly.
Yeah.
You wouldn't be able to have short queries to the oracle because you'd have to have this list of what all these.
Yeah, to make sure that you've maintained consistency, yeah, it's not clear, right? Unless the ordering is.
Right.
That's not an input of the oracle.
Yeah. So if you could say input something computing the ordering.
Function first, you're not getting much information.
Yeah. So if the ordering is computable in some interesting way, like say even in Ph or something, like without much, then yeah. So I mean, you take some non-computable ordering, I guess. Okay. Yeah, this argument wouldn't work. I'm not sure if any argument would work. But,
I guess we're in the question phase. So,
Yeah, I guess so.
Any other other than MCSP, other functions that you can prove this for, or is it some very unique kind of thing?
Yeah, so in the paper we cover all kinds of variants, so time-bounded Kolmogorov complexity, space-bounded Kolmogorov complexity, like there are different variants. So there's versions of MCSP with all kinds of different oracles, and these give rise to, so like I give you a string and I want to know roughly, like, is there a quick machine or is there a space-efficient machine which will generate the string, which with a small description.
SAT, let's say.
Yeah, there's some, so yeah, proving such a thing, or even for like bounded non-determinism set would be like super interesting. So right here, like the idea I had for a long time was like, well, I mean, because the non-determinism is not much, you just guess something at S of n, poly S of n spatial around looks hard. Yeah, it'd be an interesting question of whether, like, say, the SAT problem with, like, say, polylog bits of non-determinism, proving a lower bound like this would imply P not NP. I don't know, but it's a plausible conjecture, I guess. Okay.